Hi, well, my name's Ewan Haggerty. I got into 3D printing as part of 3D Crowd because my wife is a respiratory physio working in the Bath region, and I was aware that the NHS and the local care homes didn't have the PPE they needed. So I saw 3D Crowd on Facebook and joined, and have worn out my little Ender 3 trying to produce face mask parts for them. But this kind of crisis made me think that it might be of interest to you guys to know of some of the other potential natural disasters which could occur. And one of them is actually something called space weather, which very few people have heard about. The graphic that you can see is an illustration of how the sun changes its activity on an 11-year cycle, from being quite quiet to getting more and more active until it's extremely active, and then it decreases in activity till it becomes quiet again. Now, these are a series of images from 2 cycles ago, so we are actually now in the kind of similar situation to 2006, where things are beginning to ramp up again. Now, why does the space weather risk need addressed at all, especially if people haven't heard of it? Well, if you remember the big volcanic eruption from Iceland, which nobody can pronounce, after that happened, the government went to the government chief scientist and said, well, what other natural disasters could engulf us? And there we are, effusive volcanic eruption is in the middle. And the government chief scientist said, well, the worst thing you can possibly have is pandemic influenza. This was at the same time, roughly, as where bird flu was about, and people were very concerned that both the likelihood and the capacity for impact of pandemic influenza was going to be very high. And we are actually in that bubble right now. But the other things are things that we've all seen and have seen something about. We've got coastal flooding, we've got widespread electricity failure, we've experienced them. We've got low temperatures and heavy snow, that's also happened. Down here, we've got public disorder, we've got major industrial accidents, major traffic accidents. But up here is space weather. And space weather is what they call a tier 1 threat, which is something which is along this line. So it's likely to occur and could have a very serious effect. So I'm going to try to explain why. Right, bit of history. Let's go back to the 12th century. And this is the first actual recorded observation on the sun of something unusual happening. The Chronicles of John of Worcester. The monks there were in the habit of recording what was happening in nature in a sort of a rambling blog that they put together. And they drew a nice picture of the sun with 2 nigri pila infrasolis. So if you understand your medieval Latin, that means black spots in front of the sun. And they drew this nice picture. So they had even a bit of the umbra around a sunspot being shown there and depicted, a slightly less dark region. So likely that they saw these sunspots through a thin veil of cloud or close to the horizon. And I've seen sunspots when I've known where to look since then, when there have been big ones on the surface of the sun. So this observation is perfectly possible. This also ties in with observation that Chinese astronomers made of unusual lights in the sky at around this date. If we fast forward now to the time of Galileo, one of history's forgotten scientists is a chap called Christoph Scheiner, who is a Jesuit priest, and he is the chap who can actually take the credit for analysing sunspots properly for the first time and determining that the sun actually spun on a particular axis. Galileo, like for the telescope, gets a lot of credit, but it was actually Christoph Scheiner that did a lot of the donkey work. A little bit further forward, and this is where we're getting close to modern times. This is 1st of September 1859, and this chap, when he was a bit younger, was a sunspot watcher. He'd built an observatory in the loft of his house in South London, and his hobby was drawing pictures of the sunspots as they rotated on the surface of the sun. And he was particularly interested in this very, very large one where something unusual happened. This is his actual logbook. It's held at the Royal Astronomical Society in London, and you can see the meticulous care with which he was drawing what he could see, and these are times of crossings across a graticule in his telescope. And then he had to burst into this text where he wrote down something where he was clearly very excited for a Victorian, 2 exclamation marks. This is what he wrote. While drawing, Aurora suddenly broke out at 11:12, there being a kind of conflagration at the 2 patches A and B marked in red ink, which for 2 minutes, till 11:20, was about double the brilliancy of the usual disk. Then they faded and changed in form and position, being last seen as 2 dots C and D at 11:23. The details of the spot remained the same. So what he saw was something really, really bright on the surface of the sun, driving from this position to this position over the surface of the sunspot. If we take his drawing and use the coordinates which he'd logged and then plonk it on the surface of the sun, you can see that it's a fairly big sunspot, but it's not very detailed, and that kind of gives you a clue as to the size of the telescope he was using. It wasn't really that good, and it's possible that although he got the really darkest bits, there might have been lots more splodgy bits away out over here as well. 2nd of September, this is where the fun really started, because there was massive aurora all over the Earth, and at least in the northern hemisphere, as far down as Cuba and El Salvador, and even seen in Hawaii. There are stories of harbour masters in the Caribbean putting rescue boats out from the harbour, thinking that there must be a major ship on fire just over the horizon. The lights were so bright and so red. These are where there were recorded in the press sightings of Aurora on the 2nd of September. So that flash which Carrington saw on the surface of the sun from that sunspot took about a day and a half to travel to the Earth and do something quite spectacular. Included in the stuff that was quite spectacular, there were the beginnings of a Victorian internet. They had telegraph lines which were spanning Canada and the United States, and this basically broke down. There were batteries used at either end of these telegraph stations in order to power the signals, and enough electricity was trapped by the wires themselves and put into these battery sheds to cause them to explode, and paper caught fire. And even when the operators disconnected everything, they found that the system was still live because something was pumping electricity into the wires about linking the stations. So what was going on? Well, this is an interesting little video. It shows the sun back in 2013, and these plumes coming out of the sun are really 2 types of things. One of them is something called the solar wind, and the other one, which are these effusive bubbles of gas coming out, are called coronal mass ejections. Now, the solar wind streams out of the sun the whole time. It's a mixture of protons and electrons, and the solar wind is guided and kind of focused by the very strong magnetic field of the sun. But occasionally you get conditions above what's known as an active region in the sun, where there's an unstable magnetic field associated with the sunspot usually, which when it flips, it creates conditions for a massive amount of gas and material to be flung out from the sun with considerable force. If these coronal mass ejections have sufficient power, like Carrington's one, then they can reach the Earth in probably just under a day and a half. So the sun's doing this all the time, but it's doing it at different rates dependent on where it is in the solar cycle. This is from when the sun is highly active, so you get 3 of these coronal mass ejections on average per day. But when the sun is quite quiet, like it is now, it's more like 1 every 3 days, and it will be a weak one at that. But it's important to remember that we live in close proximity to a star. We're only like 8 light minutes away from it, and the solar weather, the stuff that the sun kicks off, will connect with us because effectively the whole of the inner solar system flies around in the outer atmosphere of the sun itself. So just going back a little, well, going further forward from Carrington's time, here's a picture of the sun as it appeared during something which was called the Halloween event. There was a large, complex, scruffy sunspot, very similar in size and configuration to the one that Carrington had seen. There was also a companion sunspot near it, which was nice and simple. It had sort of 2 dark areas, and that's because basically all sunspots are composed of north and south pole regions. And when they're simple like this, you get a nice, good, strong bar magnet effect, and it's nice and stable. But if it was all scruffy and mixed up like this, then the little sunspot components are all swirling about the whole time, and that causes the magnetic loops to break off. This X17 flare and the associated coronal mass ejection that came from it caused problems in a similar way to Carrington's effect, in that you got power grid problems in Scandinavia, Canada, and part of the USA. Basically, power transformers blew up, and spacecraft problems were caused for dozens of operators, and that's really where my interest comes in. Let's go back to the sun and look a little bit more about it. As I've said, it's about 8 light minutes from us. It's a midlife yellow dwarf star, so it's as common as chips. It's about 4.6 billion years old, and it's going to continue exactly as it is for about another 4 billion years. So what it's doing is completely normal for a star of this type. We've got sunspots, which I've talked about. The gas above the sunspots can get very agitated when the magnetic field changes around them, and that's when you can have something called an erupting prominence. An erupting prominence, if it is vigorous enough, is actually a coronal mass ejection. Solar flares are where you've got a very sudden rearrangement of the magnetic field above a sunspot, and that produces ultraviolet and hard X-rays. And when those happen, they can be bright enough to cause a mirroring of the Earth's ionosphere, which can affect high-frequency radio communications and interrupt UHF communications on the daylit side of the Earth. Coronal holes are another sort of feature. They are slightly darker patches of the sun where the magnetic field is not constrained by any structure like a sunspot, and the magnetic field just streams straight out, and that forms like a jet from which the solar wind flows. Now, the sun's always changing its features. It's always swirling about quite a bit. The rotation speed of the sun is once every 27 days. So a feature seen on this side of the sun as it rotates around takes about 2 weeks to get to that side. That's important because it's in this area, the kind of just past 2 o'clock position, which is the most sensitive part of the Earth to the sun. And the sun is a slushy ball. The equator rotates about 4 days faster than the pole does. So any feature that you've got on the sun, it kind of gets smeared and stretched with this side going, with the middle part going faster. Anyway, let's look at a video of the sun here, and there's an active region here, and look, there was a flare. If we zoom in on that, underneath here is the black part of a sunspot, but what we can see actually is the X-rays being given off by this particular sunspot region, and you can see this loop of gas which is being twisted off as a magnetic field rearranges. Now, if the sun's weird, our Earth is pretty weird as well. Inside the Earth, we've got a solid nickel and silicon core, and then around it, we've got an unusually large liquid ocean of iron and sulfur, which is in constant motion. It's got its motion because it's trying to dissipate heat up through the upper mantle. That heat comes from both the formation of the Earth and the radioactive components in the core. But because the Earth is spinning and because this is convecting, you wind up with this self-inducing dynamo effect, where an enormous magnetic field for the size of planet that we are is generated by the core of the Earth. So we've got this big magnetic field. Venus, which is almost the same size as the Earth, does not have this convective inner region because it doesn't have as much metal in its core. And that's one of the reasons why astronomers believe that the Earth was formed by a collision of two planets, one about the size of the original Earth, one about the size of Mars, and we've got 2 cores worth of planet inside our planet, and the moon is just made up of some dandruff that was left over. But this immense magnetic field around the Earth does protect life on Earth and interacts very strongly with the magnetic field and the particles coming from the sun. So here's a computer simulation that shows the magnetic field around the Earth being stretched out like a windsock and being rattled around. I'll do that again. Rattled around by changes in the solar wind speed and particles coming from the sun. Now, the aurora are what are formed by the particles getting into the Earth's atmosphere from where the magnetic field lines come into the Earth, and when the magnetic field lines are being waved around and you get that windsock effect, the magnetic field lines of the Earth sweeping through power lines and through distribution pipelines are what gives you the currents that can cause great damage to power systems and gas and oil distribution systems. So here's another little video. This is looking down from the top of the sun. So there's the Earth in orbit. And you can see that there's other boxes there. One's called A, one's called B. These are 2 satellites that were launched into a near Earth orbit around the sun. If I just repeat that video, you can see this strange balloon coming out. That's a coronal mass ejection, so that's about 1 Himalaya's worth of stellar material being launched out into space. And on the other side, this other picture, when the CME hits, you can see the particulates, which are electrons and protons getting into the detector of a camera which is observing the sun and causing all this streakiness and damage. That can really upset spacecraft electronics if your electronics are not hardened enough. Now, how lucky have we been? Well, this is 2012, and around about the time of the Olympics, which is why this is called the Olympic CME, there was a huge sunspot. It rotated away from pointing at the Earth. Then it caused a CME that blew up, and it didn't hit the Earth. It did hit Stereo A, that little spacecraft over here, and that spacecraft had to fly upside down for the rest of its life. It was so badly damaged. If that CME had hit the Earth, it could have caused massive electrical power outages, lots of spacecraft damage, loss of GPS, and it could well have been a civilization-changing event. But nobody knows much about this because it wasn't talked about. Okay, let's have a look at what's really happening with the sun in terms of the cycles. Like I said, every 11 years we've got a cyclical activity. The last cycle was cycle 24. We're off on cycle 25 now. It's just beginning to pick up. This wiggly line is what's known as the sunspot number, and basically the more sunspots you've got, the more aggressive and angry the sun is and capable of launching CMEs and flares at you. And it's actually the down slope from having got to its peak is the most dangerous part, because there's where you get most of the flaring. So it won't be for maybe the next 4 years from now that we'll get the worst from the sun. It will probably be possibly 2025 when we'll start getting hit by big events from the sun again. Now, what does it mean for all of us? Well, it means a lot in terms of our ignorance. we've only had a few solar cycles where man has been active in space flight and using space as a resource for communications and services such as meteorology and Earth observation. In that time, the Sun has had some active cycles, but as I've shown you in 2012, most of the really big ones have missed. In fact, you can do the maths backwards and show that we have had the sort of luck that comes only once in 200 years to avoid having a very, very major space weather effect which could have impacted the Earth. That's why it was so high up in the scale of natural disasters which could befall us from the government chief scientist. Now, just a little look into my domain. Each green dot is a space vehicle which has been launched by mankind around the Earth. These are the low Earth orbiters. There's another cloud, which is the medium Earth orbiters, which are like your GPS and your Galileo navigation satellites. And then there's the ring of geostationary satellites, which gives you your Sky TV and other forms of communication. I'll just play that one again. There's polar satellites, which ones you can see in this ring here. Now, different orbits in different positions within the Earth's magnetic field get different sorts of dosages from particles released by the Sun. Low Earth orbiters, because of the focusing effect of the Earth's magnetic field of the particles, can be extremely damaged. The medium Earth orbiters always live in belts of extreme radiation from trapped particles. You might have heard of the Van Allen belts. They're in them all the time. But during an extreme space weather event, then the population of these Van Allen belts can go up by at least 2 orders of magnitude, or at least 1,000 times. And the outer ring of satellites around the Earth, the geostationary belt ones, well, initially, a lot of the particles which they could get in contact with get flushed away, but as that flapping windsock of the Earth's magnetic field snaps back into position, they can get a sudden dose of electrons, which can be extremely damaging to electronics. Here's a little picture of the sorts of things I'm talking about. You've got the GEOs, those are the faraway ones, the MEOs, which we talked about, doing the navigation satellites, and all little LEOs below. You get the particulate radiation that can damage them from cumulative dosage or single event upsets, and that can break the spacecraft and cause anomalies. And events from the electromagnetic radiation of the flares of the Sun can give link disruptions as the ionosphere gets mirrored with the sudden impact of the ultraviolet from the flare. Also, for a low Earth orbiter, even if you're above the atmosphere, the flares can cause the atmosphere to heat up and expand, and that can grab your low Earth orbit satellite and slow it down enough that it can have an accelerated decay and wind up burning up in the Earth's atmosphere. So, just in case I've not worried you enough, the threats are: we can lose GPS, which is really bad, not just for navigation, but for timing, on which a lot of our systems depend. We could lose satellite communications, so we could lose our Sky TV. We could lose other forms of communication, which are to do with financial exchanges. The large change in the magnetic field in the Earth induced by absorbing this CME can cause power transformers to fail, giving us long and persistent blackouts over a large area and affecting large populations. You wouldn't want to be flying an aircraft through a period where there was an extreme part of solar weather, because you would have an extreme radiation dose, especially if you were on the polar route. And it could be the end of life as we know it, and we're all doomed. Except perhaps we're not. Science is evolving in the understanding of this. We've got the Met Office, which is the actual owner of the UK space weather risk. It produces daily forecasts of different types and alerts and warnings, a little bit like a shipping forecast, but is focused on looking at what the sun is doing. So you get pretty maps and charts and graphs, which all mean stuff if you are an operator of a space-sensitive endeavour. Now, there are 13 critical national infrastructure assets which the government worries about, and just 2 years ago, space was added as the 13th, which I think is quite appropriate. Now, if I've interested you in what I've said, there is this wonderful site called solarham.net, which is a bit like a fan page to the sun. It's got links to all of the science missions, and also along with the science missions, there are links to other sites which explain more about solar weather and what could happen to us in an extreme space weather event. So I would encourage you to have a look at it just for fun, if nothing else. And that's it.
Well, thanks very much, Ewan. So we've had a few questions. So the first one's from Neil on what should we look for in the sun to see the cycle changes over the next few years?
Okay, well, at the moment, sunspots for cycle 25 have just appeared. There is one very, very small sunspot, which is, if you like, at the bottom 4 o'clock position, quite close to the poles. Over the next 4 years, you can expect to see more sunspots being formed. And as the years advance, you'll see the sunspots getting larger and forming closer and closer to the equator. When they get to the equator, that's when we'll be at what's known as the solar maximum. And from that point on, that's when we'll start getting flares.
Okay, and we've got another one from Rowan of, can we see one of the sun's ejections with the naked eye?
I'm afraid you can't see the sun's ejections with the naked eye. The video that I showed you was taken from telescopes that were in space. They've got a special type of telescope called a coronagraph, which is when you look at the structure, it's got lots and lots of light absorbing ridges in it and a large disk that sits over the sun itself because the sun is so flipping bright. The only time that you can get to see a solar corona is during a total solar eclipse. And in actual fact, there's been some very good research recently been done on looking at photographs of corona taken during solar eclipses and analysing them for the magnetic structure. So really, if you do want to see the corona from the Earth with the naked eye, the only time you can get to see it is during a total solar eclipse.
Great. So we've got another one from Tim. Could the solar weather in 2025 cause satellites to fall out of orbit?
Very low Earth orbit ones, it can accelerate their loss of altitude. Yes, it can cause them to burn up earlier. One of the concerns that a lot of the guys that have in the industry is that access to space is becoming cheap and quite commercialized. You'll have seen the Dragon launch. You'll know about Elon Musk and his Starlink program for getting kind of like 5G delivered by satellite. This is all cheap and cheerful space where people are launching things into space that are probably not that electrically robust. At the same time, our particular generation now is so dependent on the sorts of medium we're using just now, internet. We use navigation, which takes tiny, tiny radio signals. And really, we've grown used to being able to do things without the gross impact of the sun on them. So yes, if you that event that I told you about in 2003, there were 153 satellites whose position were temporarily lost because they had changed the position due to unusual drag effects due to the expanding atmosphere. And all of these satellites had to be maneuvered to regain their orbits. and that would have cost them actual functional lifetime.
Oh, okay. As we've got one more, if the Earth was majorly hit, what would be the best way of us sending messages around the country?
The best ways of sending messages around the country if there was an extreme solar event?
Yeah, so I think if we sort of lost satellite communications because of this, what would be our backup options?
Okay, point-to-point radio communications, like mobile communications, so long as the mobile mast remained powered, would work quite well. Telegraph lines, as in the old-fashioned telegraph lines that you think of, well, we don't have many of them. It's only copper really now from the exchanges to the house. Most of the communications is done by fibre. However, they're still vulnerable by having to have a repeater about every 17 kilometers or so, which requires a source of electricity. So let's say your power goes down due to an extreme space weather event. If your mobile works, your mobile is probably the best option, so long as something's connected to the tower. Other than that, it's standing on a hill and waving flags.
Yeah. And so I guess we'd lose sort of inter-country communications almost definitely. If we...
You probably would. You'd certainly have an impact. People have looked at the Carrington event and they have said, oh, that's an example of the absolute worst that could happen. But when the Carrington event happened, it did deposit nitrates into the atmosphere, and that got wound up being polar ice, and you can see it as kind of like a tree ring band in the ice. Looking deeper into the ice, it's been shown that the sun has produced very major events which have been between 20 and 200 times as strong as the Carrington event. So although Carrington event is significant, it's nowhere near as big as the sun can produce. And kind of all bets are off as to what would happen if we had an extreme event of that nature.